Hello and welcome to the second video of the M3 chapter Circular Motion. If you like, pause the video now and complete these formulas from the previous video. Here we've got v, which is the tangential speed, and that is equal to r times omega, where omega is the angular speed and r is the radius of the circle. A for acceleration here is r omega squared, or v squared over r. In this video, we're going to be using these ideas to look at three-dimensional problems with horizontal circles. It's fairly straightforward with the notes, that's kind of it. We can use resolving forces to apply those formulas to circles with a three-dimensional element. All we do is basically balance the vertical component with the weight, and what I mean there is, say you've got a piece of string here that's fixed up here, with a weight on here going around in a horizontal circle here, then the tension in the string, the vertical component of that, will balance the weight so that there's no vertical movement, and the horizontal component of that, what I've called here the unbalanced horizontal force, will produce the acceleration needed to keep it moving in a circle. So this component here will be your F equals ma, where the A is, as we just said, r omega squared, or v squared over r, depending on what you need, and that's your acceleration for the circular motion. Jumping straight into an example that is just like this. A particle of mass 2 kilograms is attached to one end of a light inextensible string of length 50 centimeters. Now, straight away, be careful here. Don't leave that as 50 centimeters. Change that into meters. And then here we've got 2 kilograms, so that's 2g on the weight. The other end of the string is attached to a fixed point A. The particle moves with constant angular speed in a horizontal circle of radius 40 centimeters. Again, let's change that into meters straight away. The center of the circle is vertically below A, which is often what you will be told. Calculate the tension in the string and the angular speed omega of the particle. If you remember your Pythagorean triple, you can see that my diagram is not very well drawn because that makes this a 0.3 meters, which means if I make this angle theta, I can write straight away sine theta is 3 over 5 and cos theta is 4 over 5. So that when I split my tension here, we've got t sine theta, and over here t cos theta. So vertically, we can balance t sine theta with 2g, the weight, and horizontally, we've got t cosine theta, the only force acting, must equal the mass 2 times the acceleration, which we can either have as r omega squared or v squared over r, but because we want omega as part of the question, let's do r omega squared. Sometimes in a question like this you'll have to solve these simultaneously, but this is our first one. It's quite straightforward. This gives us an answer straight away because we know sine theta is 3 over 5. So that 3 over 5t is equal to 2 times, let's have 9.8, and then t must equal 32.6 recurring, and because I've used two significant figures for g, let me change that into 33 newtons, two significant figures. Now we can use t and the fact that we know cos theta to find omega squared, because we also know the radius here is 0.4. So our second equation, let me write that for now as 10g over 3 for t, keeping it in its exact form for now. Cos theta, 4 over 5, is equal to 2 times the radius, 0.4, times omega squared, and that gives us an omega squared of exactly the same thing, 32.6 recurring, but then we need omega, so let's square root that, and that gives me 5.7, that's radians per second. And again, two significant figures because I've used g is equal to 9.8. And we're going to do this same idea quite a lot in these examples. resolving vertically with a component and the weight, resolving horizontally to give us an F equals ma equation. Second example. A particle of mass m is attached to one end of a light inextensible string of length L. The other end of the string is attached to a fixed point A. The particle moves with constant angular speed in a horizontal circle. Same setup then. We've got A up here, string, but in this case we don't know how long that is. Mass, but we don't know what that is. Let's call that mg. For the weight, the string is taut, which means there's tension, and the angle between the string and the vertical is theta. So this is theta this time. The center of the circle vertically below A. Find the angular speed of the particle in terms of L and theta. This is basically doing the same thing but with algebra. So we've got t here, in this case it's cosine theta, and t sine theta this way. Resolving vertically gives us t cosine theta equals mg. Resolving horizontally gives us t sine theta. An unbalanced force is equal to mass times acceleration. And again, I want the angular speed, so I'll use r omega squared for acceleration. From the first equation, we can see that t is equal to mg over cos theta. I can substitute that into my second equation. You get mg sine theta over cosine theta. That of course will give me a tan theta. We've got mr omega squared. M's will cancel out. You can get the same result by dividing the second equation by the first equation. You get g tan theta is equal to r omega squared. But we don't want r, we want L. To find the radius, this distance here, in terms of L, we're using the same theta. So we've got L sine theta to give us r. That gives me L sine theta omega squared, g tan theta. So actually, I shouldn't really have turned that into a tan. I'm going to cancel the signs now. And that gives me g over L cos theta equals omega squared, which is fairly horrible, but it is in terms of L and theta. We get omega is equal to the square root of g over L cos theta. Third example. A car travels round a bend of radius 500 meters on a flat road, which is banked at an angle of theta to the horizontal. Okay, this one looks a little bit different. So we've got a road that is banked, oh dear, at theta to the horizontal. It's supposed to be flat, pretend this is flat. And we've got a car on here, a wonderful drawing of a car. And it's going around a bend, and the radius here, from here to the center of the circle, is 500 meters. The car is assumed to be moving at constant speed, so that's v, constant v, in a horizontal circle, and there is no tendency to slip. If there is no frictional force acting on the car down the slope when it is traveling at 90 kilometers an hour, find the value of theta. A few things to notice here. There is no frictional force acting. That's very nice. So it's a fairly simple setup. We've got the normal reaction here. That is at theta to the vertical. We've got the weight mg of the car, and the vertical component of the normal reaction force will balance with the weight. So vertically, again, we've got r cos theta equals mg, a balance there. But then we've also got r sine theta acting in towards the center of the circle, and that's providing us acceleration. So horizontally, r sine theta is equal to mass times acceleration, and this time I'll use v squared over r, because the speed we've been given here, 90 kilometers an hour, that is v, that's a tangential speed, not an angular speed. Second thing to notice is the kilometers per hour. We need to change that into meters per second. which is actually a very nice 25. So we know the radius is 500, and we know the velocity here is 25 meters a second. M over here, M, R, and R, they're going to cancel out if I divide this equation by this equation, which will give me sine theta over cos theta. So we're going to have tan theta is equal to mv squared over r divided by mg. That cancels. We know v is 25, r is 500, and again I'll use g as 9.8, and that has to equal tan theta. Putting that all on my calculator gives me 7.3 degrees. Again, two significant figures. Next example. A particle P of mass m is attached to two strings. The strings are attached to fixed points A and B respectively, where A is vertically above B. The strings are both taut, and P is moving in a horizontal circle with constant angular speed that. Both strings are 0.5 meters in length and inclined at 60 degrees to the vertical. Okay, if they're both inclined at 60 degrees to the vertical, and they're both taut, A is above B, then we've got a setup that kind of looks like this. They're both 0.5 meters in length, so the particle is going around horizontally like that between the two. Calculate the tension in the two strings, and then we've got an extra part. Okay, we'll do this bit first. So I'm going to redraw that for a second. A, B, and then over here, center of the circle here, and this is 60 degrees, so is this, and this is 0.5 meters, and so is this, which means we can calculate the radius. The radius is 0.5 times sine of 60, which is root 3 over 4 meters. Okay, that's going to be useful. Both strings are taut, so we've got a tension here, call that T1, tension here, which is perhaps obviously different, T2, and we know the constant angular speed is 2 root 3g. And here we're going to do the same thing as we've been doing. We're going to resolve vertically. That gives me T1 cosine of 60 must equal, I didn't put the weight on, mg plus T2 cosine of 60, because T1 is obviously acting up a little bit as well as in, and T2 is obviously acting down and in. So T1's component must balance the weight and T2's component vertically. Horizontally, T1 sine of 60 plus T2 sine of 60, they're both acting in the same direction. Horizontally, that must equal mass times the acceleration, which is r omega squared, using that one because we know what omega is in this question. We've also already worked out r down here, so I can put those in. Mass times root 3 over 4 times omega squared, that's nice, that's a 4 times 3g, so the 4's cancel. I've started on this one, so let me keep going. On the other side we've got root 3 over 2 t2 and root 3 over 2 t1, so all the root 3's also cancel out. Times everything by 2 to get rid of these halves on the left, gives me t1 plus t2 is equal to 6mg. In the other equation, even nicer, because cos 60 is a half, so we've got t1 over 2 equals mg plus t2 over 2. Again, times everything by 2, get rid of those fractions, we get t1 is equal to 2mg plus t2. Substitute that into our other equation down at the bottom here. T1 is 2mg plus T2 plus T2 from this equation has to equal 6mg. So 2 lots of T2 equals 4 mg, so T2 must equal 2 mg, and T1 is equal to T2 plus 2 mg, so that is 4 mg, double checking, 4 mg plus 2 mg does equal 6 mg. So there's the tension in the two strings, doing our usual resolving horizontally and vertically. Now we've got a second part, which said the strings will break if the tension in them exceeds 8 mg. The angular speed of the particle is increased until the strings do break. State which string will break first. Well, we've just said that T1 is 2 mg bigger than T2. Whatever these are, this still holds. So T1 will obviously hit that limit first. Then we need to find the maximum angular speed of the particle before the string breaks. So if it breaks when it exceeds 8 mg, then what we're doing here is we're making T1 equal to 8 mg. Again, this equation here is still true, so T2 must be 6 mg. And we want the maximum angular speed, so I'm going to use this equation here. Most of this hasn't changed. We're still using sine 60, the radius is still the same, the mass is still m. All that's changed is T1 and T2. So we've got T1 sine 60 plus T2 sine 60 still has to equal m root 3 over 4 times omega squared. Putting in the tensions that we know, we've got 8 mg times root 3 over 2 plus 6 mg root 3 over 2 equals m root 3 over 4 omega squared. Again, we can cancel all of these. I can also cancel these, get a 2 there, cancel all of the m's. That gives me 14g on the left, multiply by this remaining 2 here. Gives me 28g equals omega squared. So omega is equal to the square root of 28g. I'm going to leave it like that. If you want it in decimal form, it would be 16.56 ... or 17 to two significant figures, but I like the exact format there. Next example. An aircraft of mass 2 tons, that's 2,000 kilograms, flies at 500 kilometers an hour. That's a rather awkward 1250 over 9 meters per second on a path that follows a horizontal circular arc in order to change course from due north to due east. The aircraft turns in a clockwise direction, which is good because that's what I automatically assumed. So it's going 90 degrees. It takes 40 seconds to change course, with the aircraft banked at an angle alpha to the horizontal. Banked just means it's inclined alpha to the horizontal here. There are the wings, there's the back, there's the front of the plane, going around like this. You can tell my artistic skills are legendary in my classroom. Calculate the value of alpha and the magnitude of the lift force perpendicular to the surface of the aircraft's wings. So the lift force is what's providing all of the necessary forces involved here to balance the rather substantial weight, 2000 g. We've got F cosine alpha, and then providing the inward force for the acceleration as we turn around in the circle, we've got F sine alpha. Now we get to a slightly fiddly bit specific to this question. They haven't given us a radius, and we're going to need a radius, but they have given us enough information to find it. We've got the speed here, tangential speed, and we've got the fact that it does a quarter turn on a circle. It takes 40 seconds. With the speed and the seconds, I can work out the distance it travels, which is the arc length, and from the arc length and the fact that this is a 90-degree turn, we can work out the radius of the circle. and all of that is just on the side to find the radius. So over here in blue, I've got v is equal to 1250 over 9, and that is equal to distance over time, which is 40 seconds. So my distance traveled is equal to 50000 over 9, and that is the arc length, which is a quarter of a circle, quarter times pi times diameter, to r. So r is a really awkward 100,000 over 9 pi meters. Back to the usual things now. We resolve vertically, giving us f cos alpha is equal to 2000 g. Resolving horizontally, f sine alpha in our f equals ma equation, 2000 for the mass. Acceleration, I'm going to use v squared over r because we know v is this awkward thing here. And of course we know r on the right hand side in blue. As we've done on a couple of the others, divide the second equation by the first equation, gives tan alpha is equal to 2000 times v squared, which is 1250 over 9 squared, all divided by r, which is 100,000 over 9 pi. We're also dividing by the 2000 g from the first equation. Now that's pretty horrible, but they are all things that we know using pi on my calculator, and g is 9.8, gives me an alpha of 29 degrees to two significant figures. From there I can calculate the lift force perpendicular to the surface of the aircraft wings just by putting this into this equation here. So we've got 2000 times 9.8 divided by the cosine of this gives me f and that is a fairly chunky 22,431, which I should round also to two significant figures. There we go. Approximately 22,000 newtons at an angle of 29 degrees to the horizontal. One final example. A hollow right circular cone is fixed with its axis of symmetry vertical and its vertex v pointing downwards. So we've got a cone like this. A particle p of mass 25 grams. Now I don't like that because that looks like 25 g to me, but it's not. 25 grams, 0.025 kilograms, moves in a horizontal circle with center C and radius 0.27 meters. So let's say it's here because it's on the rough inner surface of the cone. It's going around on the inner surface of the cone like this, center C, and here to here the radius that we're interested in. We don't care about the radius of the cone if the particle is not at the top. We care about this radius here, and that is 0.27 meters. P remains in contact, this is particle P, remains in contact as it moves with constant angular speed omega and does not slip. The angle between V, which is the vertex, and P and the vertical is theta, such that tan theta is equal to 0.45. So if I end up with sines and cosines, I will want to divide to get my tan theta there. The coefficient of friction between the particle and the cone is 0.15. Find the greatest possible value of omega. Key starting point here is if we want the greatest possible value of omega, imagine you're holding this and you're twirling it around. This particle, the harder you twirl it, is more likely to fling up and out of the cone. So if we've got the greatest possible value of omega, where it doesn't actually slip anywhere, means the friction is maximum and it's acting down the surface of the cone. So our friction here is equal to the maximum friction, which is mu times r. R, of course, perpendicular to the surface of the cone here, the normal reaction force, and often in statics we would resolve parallel and perpendicular to the plane, but we still need our horizontal force for F equals ma towards the center of the circle, and we still have the weight acting vertically downwards, 0.025 g. This way, our inward force producing our acceleration for the circular motion. So still stick with horizontal and vertical here. Vertically, we've got a component of r, and that is r sine of theta equals the weight plus the downward component of friction, mu r cosine of theta. So you can see this is getting a little bit more complicated than usual. Horizontal, we've got the unbalanced force producing our acceleration, which is r cosine of theta, plus the horizontal component of the friction, mu r sine of theta, and that has to equal our mass times our acceleration. And seeing as we want to find omega, that of course will be r omega squared. Now this is looking fairly horrible, but let's take note. We've got an r cos theta, r sine theta, r sine theta, r cos theta. Been given a little clue in the question, tan theta. So I'm going to move this term to the left and then divide through everything so that I've got all of my cos sine thetas and my r's together dividing one another. So if I rewrite that, let's have r sine theta minus mu, which I know is 0.15, r cos theta divided by the left-hand side of the second equation, r cos theta plus 0.15 r sine theta. On the other side, from the first equation, we've still got 0.025 g, and here 0.025 r omega squared, which makes me dislike this 25 grams even more because we didn't even need that. That's going to cancel out. Now looking at this left-hand side, all four terms have an r. That's nice. They can all cancel. Then we can divide each term by cos theta, because here that will produce a 1, and here as well, and here it will produce my tan theta that I know in an exact form. Same here. So dividing each of these terms by cos theta gives me tan theta minus 0.15 over 1 plus 0.15 tan theta. Over here we've got g, which of course we know, r, which we also know, 0.27, and the one thing we don't know now, omega squared. Rearranging all of that and using tan theta is 0.45 gives an omega squared of a suitably horrible fraction, 20923 over 162. And then when I square root that, I should put it into decimal form because that's already using g is equal to 9.8. So I can't leave it looking exact. And the square root of that gives me 11.364 ... So to two significant figures we've got 11, and that's omega, so that's radians per second. And that is the greatest possible value of omega. Final answer to the final example. You can now have a go at questions from exercise 2C. And maybe I'll see you in the next video.